Picking up where we left off, we found the distribution factors. So now let's jump into the moment distributions. Start with the dead load. We had 103 pounds per square foot of dead load. Tributary width is 29.5 feet. So as a line load, we have 3.039 kips a foot. We figure out the fixed end moments. And I might go a little faster here because lots of this is exactly what you've already done. There's a few things that are going to be unique to what we do in two-way slabs, but a lot of it, most of it, is just what you've already done, what you already did in the homework assignments and what you did in the beam project. So we calculate the fixed end moments. Remember, they're very close to WL squared over 12 because the columns, we got a three-dimensional system. The slab itself is wide and floppy, and the columns are not particularly large, and they're somewhat incapable of really fixing the system at least at the ends. So that's why we're going to have a more flexible system. So we calculate fixed end moments. I have a completely symmetric system. So this moment distribution, probably not a great thing for you to follow when you do your moment distribution, because I don't think I'm going to give you a completely symmetric system. When you write a book and do an example, you can make your example really, really easy, just like I did to do, and then give out homework assignments that are harder. And that's the American way. Okay, so you'll notice a few things. The moment distribution actually takes a little longer to converge. You could call it converged down here, but it's not really getting there until you've gotten about this far. That's because the columns aren't taking out much of the moment. The slab itself, these are higher distribution factors than we had in the beam analysis. Maybe not this one, but so anyway, you just a little bit more moment distribution to converge. It converges fairly quickly. We're at some larger numbers, and we get to some much smaller numbers pretty quickly. But just the point is that the columns aren't nearly as stiff and doing as much work and taking out as much moment on each distribution as they did in the beam example. So just like we did with the beam example, we figure out the center line moments and shears and reduce the moments based upon that shear diagram to the face of column. So in this particular case, we actually had a negative moment at the center line, but it becomes a positive moment by the time we get to the face of the column. So once again, we have pretty flimsy columns in a floppier 29'6" wide beam. We are going to have a jump. The jump, just like it was in the beam analysis, is what the column is taking out. Not a huge amount, though. Okay, once again, because I wrote the example in the book, I got to make things easy for myself. And lo and behold, I made the dead loads and the live loads, and you'll see in a second, even the equivalent loads, all proportional to the dead load. So I have the same live load is in span 1 as it is in span 2. The same balance load you're going to see is the same in span 1 and span 2 and span 3. Sorry, I should have added span 3 to all those. And it was a symmetric system. So I'm only going to have to do that one moment distribution, and then I'm going to scale all the others. That's unfortunately not going to be what you can do. I'm actually going to make you do the work, and I'm sorry. Not sorry, but it's good practice. You probably won't do this again. So anyway, I have the live load shear and moment diagrams. Those were just a factor of 38.8% of the dead loads. So everything you saw in the dead loads, this is 38.8% of that. And the balance loads were actually constant in all three spans. That's highly unusual. I'm not even sure I set out to do that when I did this example, but it turned out that way, and that was lucky for me, because now even the balance loads are just a proportion of the dead loads. So you get the point. So anyway, let's see how I did. 143.9, the dead load at the left side of the first interior joint. Span 1, left side of first interior joint. 143.9. Let's see if we can remember this. At the other side of the joint, 168.1. So 143.9, 168.1. 144.0, 168.1. You know, that never gets old for me. I don't know why, but I like doing the moment distributions, reducing them to the face, and rushing to see how I did. And did okay. And since the dead load was okay, it's pretty much an assumption that the live load and the balance loads are going to be the same, because I just proportioned the dead load. So, okay, so now we have the dead load moment, the live load moment, the equivalent load moment or balance load moment. We don't skip live loads, by the way, in two-way slabs. So it's not like we're taking a shortcut or doing something the code doesn't allow. You have to have very high live loads to have the code kick in a requirement that you skip those loads. So because the panels are so large, it's assumed good enough if we just apply the uniform loads without skipping the live loads. So the live loads are going to be the same: max negative, max positive. So just like we did in the beam example, those are all unfactored. We're going to check stresses. So just like in the beam example, I want you at each location, face of column, at the columns, to get the maximum dead load, maximum live load, maximum equivalent load, add those up. Within the spans, you've got positive moments, dead and live, negative equivalent loads. Post-tensioning is pushing back up on all this. So we have a net moment there. Same thing, but notice that this is the largest one. 125.45, span 2, column face. So to check stresses, the section modulus is the same, top and bottom. So really what I'm doing here is just grabbing the worst case. If I can check that, and if that works, it's going to work everywhere else, because I don't have, like I had in the beams, a small section modulus to the bottom and a large section modulus to the top. I've got the same. So in this case, 3,776 inches cubed. I'm working with 169 psi average compression. So when I go and check this number, the stress at the top, M over S, and even if I got the top or bottom wrong, it wouldn't matter because they're the same, minus the F over A, 230 ksi in tension, and the maximum compression, which we really never check, but there's going to be a reason to keep track of these, and I will get to that point later. But the maximum bottom stress at that location, M over S, negative, minus F over A, 568 psi in compression. So I do check the maximum positive moment stress, but and I'm doing this because it's going to matter a little bit later. So it wasn't a maximum that I'm looking for, but this is for a different reason. So I find the maximum positive moment tensile stress, calculate that to be 164 psi in tension. Important, in tension. And then I actually need, and this is important, but there's a surprise coming later. I need to know what the compression is at that same location, and I will show you why later. So I've got at the maximum positive tensile stress. You're actually going to need to do these at each positive location in your actual design and actual practice. But I'm doing this to make a point. We've got tension on the bottom, compression on the top. So let's check allowable service stresses. While beams and slabs got the benefit of going to 7.5 square root F prime C, two-way slabs never got that increase, and they're not going to. Doing an equivalent frame, it was decided that 6 square root F prime C should be the maximum because we are using an average. We're using an average moment over the design width. In reality, the finite element method would show you that you have increased moments as you approach the column, decreasing substantially as you get to the midspans in the opposite direction. Our analysis is doing an average of those two. So we've come up with an equivalent frame, negative moment, and a positive moment in the spans, negative moment at the supports. But they're averages, so it's as long as you keep your stress less than 6 square root F prime C, the assumption is that as you approach the column, you're going to have a higher stress, but you will not exceed cracking. That's the theory. Now, also, the reason I was doing this cloak and dagger stuff with the positive moment stress is that the code is going to require that any time we exceed 2 square root F prime C in the positive moment region, we're going to require bonded reinforcement. Additional bonded reinforcement will be required. So we're keeping track, even though we are well below the 6 square root F prime C, we're actually keeping track also of where we exceed 2 square root F prime C in the positive moment regions. 2 square root F prime C for the 5,000 psi concrete is 141 psi. We've exceeded that, so we are going to require additional bonded reinforcement, and we will get to how to calculate that a little bit actually in the next lecture. But it's important that we kept track of it right now. And believe it or not, we not only need the tensile stress, we actually need to know the compressive stress at that same location on the opposite face. You'll see why. So we can verify those service stresses. $230 on top, 164 on the bottom. $229 on top, 164 on bottom. Pretty close. Pretty good. Okay, so once again, just like with the beam, once we've established that we satisfy stresses, the force and profile, the pre-stressing is now set. It's locked in, it can't change. If we change that, we have to start all over. We'd have to start the whole thing over, which we don't want to do. We're not going to do. So that's now a given as we work our way into the flexural strength design and the punching shear checks, so which are also strength designs. So much like the beam, at the support we anchor at the center of gravity. So whatever we got in the equivalent load moment is also our secondary moment at that location. Okay. So go into the first interior support. Look at this side of that. At the center line, at the joint, the primary pre-stressing moment is F times E, and you've calculated that enough times in this course that you don't need me to explain it. But the primary pre-stress moment's 109.82 foot kips at this location, center line. So the secondary moment is the equivalent load, just like it was, minus the primary pre-stress moment, and we actually get a negative 1.5 foot kips. The right side over here of B, the equivalent load moment was 129.31 foot kips, tension on the bottom. The primary pre-stress moment at the center line, still the same, 109.82. We're just looking at the center line. So the secondary moment on the right side of the interior joint, after the column has done its work, is 19.49 foot kips. Now that, because I have a symmetric system, is just going to be constant. There's no reducing that one to the face. These two do actually get reduced to the face. And we're talking about very small numbers, so very small reduction to the face. Kind of lose a little accuracy when we get down to small numbers like that. But keep an eye on this 19.49. Those were the small secondary moment numbers. 0.15, 0.13 was what PT data got. 1.47, 1.44, pretty good. But now we're at 19.61, where it's becoming more significant. And that, I calculated 19.49. So we're close enough for government work and the things that we're doing. But notice that this, again, PT data agrees with us. This is constant. I have a symmetric system that I gave myself because I get to pick what I want to do. Okay, back to demand moments. Same exact thing. Nothing different about what we did in beams. We have 1.2 dead load moment, 1.6 live load, and 1.0 secondary moment. We come up with the term M demand because the code doesn't have one. And I'm just going to show you what this is because I think you've done it in the homework assignments, you did it in the beam project, and you really don't need my help right now multiplying 1.2, 1.6, and 1.0 times the numbers you already have. So we're coming up with demand moments. Supports B and C at the exterior side, so the span 1 side and the span 3 side, 263.7. Supports B and C on the interior side, both to the span 2 side, 286.66. So let's look for these because that'll be fun. 263.74, 286.66. $286.66. 286.6. Good enough. Got myself lost there for a second. I've brought that first page back because there's a reason. I want to talk about it in a minute. But okay, so we see where we're going. It's supposed to be C exterior side, 263.74. 263.52. Sorry about the flying all over the place. Looks like it works though. Looks like our distribution factors were correct. Our moment distribution was correct. The numbers we're getting are correct. So these are the demand moments. I'm going to come back to that in a second. So I'm going to focus on the negative moments, grids B and C, and for the positive moment in span 2. Probably what I'm going to have you do too. Just pick a maximum location at a negative moment, design that, show me that you can calculate the minimum bonded reinforcement at that location, and then check that to see if that works. It's very similar to what we did with the beams. And by the way, if you have a good design and you have the right slab thickness or beam depth, most of your design will work using minimums. That's a real beauty of post-tension concrete, is the vast majority of the entire floor system, one-way slabs, two-way slabs, and beams, are based on minimums, and that's what your bonded reinforcement should be. Every once in a while we have to add some more for strength, but in only select locations. So first thing we're going to do is look at the minimum bonded top reinforcement. I'm going to look at the negative moments reinforcement at grids B and C at the maximum side. So ACI 318 says, and this is where I'll slow down a little bit because this part's different than what we did with the beams. We did with the beams in one-way systems, we had 0014 times the area, concrete and tension. We have something entirely different here. We have a minimum amount of area of steel of 0.00075 times ACF. Now let's be careful here. ACF, the larger gross cross-sectional area of slab beam strips in two orthogonal equivalent frames intersecting at the slab. Let's say that again. It's the larger of the two intersecting equivalent frames. So in other words, whatever you calculate at a column in one direction as the minimum reinforcement is going to be the same exact minimum reinforcement that you need at the other direction. That's why I brought in this. We are going to look at an interior column, but the minimum is going to be based upon this area times the slab thickness, or this tributary area times the slab thickness. And whichever one is larger is going to determine the top steel in both directions over that column, not just in the direction that we're doing this analysis. So let's get at it. We know that we have a tributary width of 29.5 feet in the one direction. In the other direction, so that's here. So that's easy to calculate. 29.5 times 8 is going to be one of the two things we're checking. In the other direction, we have a 30-foot span and a 15-foot span. A 15-foot span and a 30-foot span, and we're looking at this distance. That's 22.5 feet. It's less substantially than the 29.5 feet. So the 29.5 feet multiplied by the slab thickness of 8 inches is going to be our ACF. And that's going to apply in both directions. So ACF, 29.5 feet times 12 times 8, 2832 inches squared. Multiply that by 0.0075 and come up with 2.12 square inches of steel as a minimum requirement over those interior columns. Five number sixes, which is very typical in our 8-inch slabs that are going about 30 feet. That's what we calculate over and over and over. 29'6", 28'6", somewhere in that range. Seem to always land at 5 number 6s. That provides 2.2 square inches of steel. So, tight design, good design. So in both directions. Now, we will end up using, as you can see in this picture, in the banded direction, we're grouping all the banded tendons kind of right over the column. Those tendons are 1/2 inch diameter. It makes sense to use number 4 bars in that direction for the rebar, and that's what we do. So they're all in the same plane, they're all the same thickness, they're all running over the perpendicular steel at the same height, creating the same cover. So we try in the thinner slabs to use number 4 bars parallel to the 1/2 inch diameter banded tendons. It's a nice clean layout. In the other direction, we'll use the 5 number 6s. So those are on the bottom of the banded uniforms. Of the banded tendons. So they're effectively being the support bars for the number 4s going this way and for the banded post tensioning. So what you can see here is we group the 5 number 6s really tightly, and those literally do just become the support for the banded tendons going by. And then we space out a little farther the number 4 bars. But be very careful. This minimum amount of steel is required to be within 1.5 H of the face of the column on each side. So you can't distribute this out very far. You've got basically the total width of the column plus 3 times the slab thickness to get this minimum bonded reinforcement in. So you got to be careful about that. Make sure your typical details reflect that. ACI 318 8755.1b says that the length required for the minimum bonded negative reinforcement is 1/6 of the clear span. So clear span being face of column to face of column. In span 2, that turns out to be 4.75 feet. We add half the column and we get 5.5 feet. So in this direction, on this side, 1/6 of the clear span, and then with the addition of the column dimension, gives us 5.5 feet. Doing it in the opposite direction, we have only a 15-foot span. We're looking at the clear span between those, the L/6, plus the dimension of the column, 2.25 feet plus the 9 inches gets us to 3 feet. Now, again, be careful. You can lay it out exactly like this. You are hopefully going to get shop drawings back if you do that reflect this exactly. Whenever you have different tributaries to each, or different spans, to each side, you potentially are going to have different minimum lengths, as long as you didn't need more for flexural strength. We don't call it out this way. We've just seen enough shop drawings, seen enough field placement that we just take the 5.5 and double it. So we would call out an 11-foot bar and let them just center it on the column. Much more likely to get what you want if you assume they're going to center all the bars on the column. And what has happened to us when we've tried to be a little cuter in some of the design builds, try to skin the cat a little bit and only come up with a bar that's 8.5 feet, is that what happens is they'll just center this bar, this 8.5-foot bar, on the column, and then we won't have the code required length going into the longer span, and that's a problem. So my suggestion is to just figure out the longer length that you need on one side and double it. You can do whatever you like. Okay, I am going to stop this lecture here, and it's enough for you to absorb, and I will pick up where we leave off here in the next lecture.